Okay, problem 1, homework 11. So problem 1, I'm just going to read it. So let x of t be a wide-sense stationary real random process whose autocorrelation function is periodic with a fundamental period t. So the autocorrelation is periodic. That's something to keep in mind. So because the autocorrelation is periodic, r of tau plus kt, any period, is the same as r of tau. So if I have r of tau plus some period, it's going to be the same as this because it's periodic. So this is a very important piece of information that they give us. Okay, show in this case that the least mean square error linear estimate of the value of a sample function at a time which is an integral number of periods away from an observation instant is equal to the observed value. Okay, so let's break that down. So our function is this, x of t. The function, an integral number of periods away, can be represented by x of t plus k big T, where big T is the period. So this is x at a integral number of periods away. So you know, if I have this, if k is 2, it's 2 periods away, 3, so on. So they want us to estimate in the least mean square error linear. They want us to estimate what this will be. So basically they want us to estimate what this will be in the future. So the estimate is designated by this x hat. By the way, I stopped putting the vectors here. These are all capital X's. I just stopped putting the vectors because it was just a lot of work. So this x with the hat represents the estimate of x, an integral number of periods away, and it's the least mean square error linear estimate. So we can represent that the way that this estimate is in this form. Some constant a times our function, which is WSS, plus another constant b. It's a form of a line, basically. So this will give us the estimate of what this what this will be at an integral number of periods away. The problem is asking us to show that this, an integral number, the estimate of this, an integral number of periods away, is just going to be the original function. So how do we do that? Well, the error is given by this equation, which is the expected value of the difference between the actual value of x t plus k big T a period away, and the estimate. So the difference between the real value and the estimate squared, and it's the least mean square error. So we have to square it. So what we have to do is we want this error to be as low as possible because they want us to find the least mean square error. So that means when this error is absolutely minimum. So the way we do that is we take the derivative of e and set it equal to 0. So we have to be careful though, because x hat has a and b. So we have to take a derivative of e with respect to b and then with respect to a. Right? Because we don't know anything about this guy. All we know is this guy. So we can write, I'm just going to write it again. E is the error is equal to the expected value of x, this is just a regular function, minus this guy. So this is going to be a big X of t plus b. Right? We don't know anything about this. All we know is what we're estimating. And in order for this estimate to be the smallest possible estimate, we need the derivative of e with respect to these variables to be as close to as small as possible. So we have to do the derivative of e with respect to a first, because this is, we don't know what this is. We need to solve that by setting this equal to 0. And then we have to do the derivative of e with respect to b set it equal to 0, and solve for b. And these constants that we'll find for a and b will give us these constants, and will give us the least mean square linear estimate of x of t at an integral number of periods away. So let's get started. So let's take the derivative of e with respect to b first. It's a little easier. So we have dE dB, which is equal to 0. We're setting it equal to 0, is equal to expected value of. So we bring down the 2, and we have a minus from here. So that's why I have minus 2, and then we have x t plus k big T minus a x of t plus b. Right. Okay. So we can pull out the constant, and we can distribute the expected values. So we have 0 equals minus 2e, expected value of x of t plus k big T, minus expected value of a x of t plus let me make sure I didn't make a mistake. We gotta be careful here. Like this, because the minus sign is distributing through. So this should be up here. Okay. So now we can get rid of this 2, divide both sides by minus 2, this goes away. So we're left with 0 equals expected value of x of t plus k big T minus a expected value of x of t minus b. So now, because x of t is WSS, we know that the expected value of WSS function is always equal to a constant. So this guy, so expected value of x of t plus k big T is equal to this expected value, which is equal to some constant which I'll call eta x. So now we have, so this is just sort of like an aside here. And now we have 0 equals eta x minus a eta x minus b. So from here we can see, if we move b to the other side, that b is equal to eta x minus a eta x. So we have our b. Now we need to find our a. So let's take the derivative of the error function with respect to a now. So d e d a equals 0. We're setting it equal to 0 because that's how we minimize. So what are we going to get? We're going to get expected value of, so if we come back here, we bring down the 2, and then in front of the a we got the minus x of t. So we have to have minus, we have a 2 and then a minus x of t. So we have minus 2 x of t. The minus comes from the x of t, from the chain rule. So we have big X, t plus big kt, minus, I'm just going to do it like this because I confused myself before, minus b. Okay. So now we have to plug in here what we have for b, right? So we have b, you can plug it in. So we get 0 equals, you can take out the 2, which we're going to throw out anyway because it's, you know. So we have x of t times x of t plus k big T minus a x of t minus now b. So we have eta x plus a eta x because the minus sign distributes. So we can throw out this minus 2 because we can divide both sides because there's 0 here. So we have 0 equals. So now we have to distribute this x along. And then take the expected value. So we have expected value of, we have x of t plus k big T minus a expected value of x of t. This is a constant, so minus x. And then we have plus, oh, I forgot. We should have here, because there's an x, I forgot to distribute the x. Let's see. I missed something. Need to distribute the x. So this should be an x squared here, because the x is here squared. Minus, this is a constant, so it comes out, but we have an x of t, so we have expected value of x of t plus a to x, but then we have expected value of x of t. Right. So this we showed was a to x. This was also a to x. So we can write minus a so here we have, this is a to x, so it's a to x squared plus a to x squared, because we have a to x times this, which is also a to x. So this becomes the auto correlation R of k big T. So this guy becomes R of k big T. Now why can I do that? Because this is a WSS and the autocorrelation is only a function of the difference, and the difference between these two is KT. So I have that. Now here I can pull out an A from these two. So I have minus A. Now I gotta be careful because I took a minus sign out. Expected value of this. And this is a minus because we want a plus a to x squared, and then this is here. This is equal to 0, by the way. Okay. So this is also equal to 0. We want to find a, so we move this to the other side and divide by this big guy. And what are we left with? A is equal to R of k big T minus a to x squared over this guy. Minus a to x squared. So A is equal to, the top is the covariance of KT, and the bottom is the variance of x. So we have that. So we can write that for the least mean square error in the linear sense, that the best estimate is going to be this. So this is A, so it's covariance KT over sigma x squared times big X, right? So this is A times X plus, and then we have our B, which was a to x minus a to x. So now this was just, there was a hint, so this shows proves the part that was in the hint. But we want to take a look at R, right? Because R of t is periodic, the autocorrelation is periodic, we can say that R of this should be a tau, is equal to R of tau plus kt, which is equal to R of kt, which is equal to R of 0. right? Because it's periodic, so it doesn't matter. So, we can write from here that R of kt, because R is periodic, we can write it as R of 0. So we have, this is just looking at A. So we have R of 0 minus eta x squared over expected value of x squared. So this is A. Minus eta x squared. Well, what is R of 0? R of 0 is expected value of x of t squared. So we can see that the numerator and the denominator cancel and we get 1. So A is equal to 1. Now what happens? Let's go back here. If this is 1, so this goes to 1. A is 1. By the way, I should have put this as A here, but I didn't. This also goes to 1. So what happens? This cancels with this, and we just have x of t. So we have just shown that the best estimate, best mean square error linear estimate, x hat of t plus k big T, is equal to x of t. And that completes the problem. I made a mistake, a small mistake in my solution. When I get to here where I'm talking about how the autocorrelation is periodic, this is true because in order to be periodic, we have this kt, so tau plus an integer away is periodic. However, this is not equal to this. However, this is still showing that R is periodic because this is the same thing as this when tau is equal to 0. So when tau is equal to, if tau is equal to 0, R of 0, R of kt is still periodic. With this is it's still periodic, so R is still periodic. So this is just the case where tau is equal to 0. The rest of the proof is the same because if it's periodic, they're not giving us a specific tau, right? All we know is that it's periodic. So we have R of kt. So if we have R of kt and we know it's periodic, that means this R of kt is equal to R when k is equal to 1. So R of t, R of 2t, R of 3t, so on. They're all equal. And also when k is equal to 0. So that's why we can say that R of kt is equal to R of 0, because they are periodic. And that's what, this is just a general way of showing they're periodic. But this is the way that they're periodic in the problem. And then the rest of the proof follows the same.